So we've sort of given a basic outline of the Schrödinger model, and we've identified that the orbital of an electron can be described by three quantum numbers, n, l, and ml. So what do they all mean? What do those numbers refer to? And what do we mean by the orbital of an electron? So a good way of thinking of an orbital is it's the region of space where we are most likely to find the electron. The individual quantum numbers all have their own meaning. So we have three of them. The first is what's referred to as the principal quantum number. It's always a positive integer, so 1, 2, 3, 4, 5, 6, or 7. L is what's referred to as the angular momentum quantum number, and it's an integer that ranges from 0 up to n-1. And ml is the magnetic quantum number, which is an integer that ranges from -L up to +L in increments of 1. So a valid orbital will have a valid set of n, l, and ml. So something like n equals 2, l equals 1, ml equals -1, that would represent one valid orbital, because those values of n, l, and ml are allowed according to these three rules that we have describing them. So the principal quantum number, n, is the same quantum number that we saw in the Bohr model. That describes the size of the orbital. It's going to give you the approximate distance of the electron from the nucleus. This is sometimes referred to as the atom's energy level, or sometimes referred to as the shell number. The angular momentum quantum number, that's the L value, that corresponds to the shape of the orbital and is sometimes referred to as the subshell type. So L equals 0 corresponds to a subshell type of S. L equals 1 refers to a subshell type of P. L equals 2 refers to a subshell of type D. And then L equals 3 refers to a subshell of type F. And so these letters are probably familiar to you from Chemistry 139. And hopefully, perhaps you remember that an S subshell is different in shape from a P, which is different from from a D, which is different from an F. So the angular momentum quantum number describes the general shape of the orbital. The magnetic quantum number, ml, describes the orientation of the orbital in space. So how it is directed with respect to the x, y, and z values. So depending on the value of L, you can have multiple values of ml. So for an S subshell, there's only one possible orientation. For a P subshell, or for a p orbital, there are three possible orientations. For a d subshell, there are 5 possible values of ml, and for an f subshell, there are 7 possible values for ml. So those numbers are probably familiar to you: 1, 3, 5, and 7. Now, it turns out that in order to describe exactly what's happening with the electrons in an atom, we actually have to consider a fourth quantum number. And this was discovered through an experiment that's referred to as the Stern-Gerlach experiment. And what they found was, if you take a stream of hydrogen atoms that only have one electron, and you pass them between a magnet where we have a north pole above them and a south pole below them, and as those atoms with their one electron come along, what happens is they behave as though they are magnets, with half of them have their south pole pointing up and half of them have their south pole pointing down. That is, the atoms behave as though they are magnets that have where their magnetism is quantized in either 1 or 2 values. So the electrons, which are tiny little charged particles, they behave as though they are spinning. And when charged particles spin, they create magnetic fields. However, it looks like the spin is quantized. The spin of the electrons can take only 1 of 2 values. They are spinning in such a way that they make the atoms get deflected up, or they're spinning in such a way that they make the atoms get deflected down. So an electron spin is described by this 4th quantum number called ms. And ms is the spin quantum number, and it has only 1 of 2 values. It's either +0.5 or -0.5. So the spin quantum number is not describing where the electron is. The spin quantum number is describing how it is spinning. So this leads us on to a principle referred to as the Pauli exclusion principle, which was formulated by a guy called Wolfgang Pauli. Wolfgang Pauli, I don't know, there's something about him, he just looks kind of fun. I'm going to read a biography about this guy, but he's really excited about whatever he's got going on in this pipe over here, and he just looks like a fun kind of guy. I want to learn more about him. And what Pauli came up with was this principle that states no 2 electrons in the same atom may have the same set of quantum numbers. So what this means is that if N, L, and ML are the same, then MS must be different. And if you keep in mind that N, L, and ML describe an orbital, and then MS describes how it is spinning, what this really means is that for a given orbital, you can have 2 electrons in it, but those electrons must have opposite spins. The maximum number of electrons that you can put in an orbital, that is into a region of space where we have the same N, L, and ML, is 2, and those 2 electrons that go in there have to have opposite spins. Now, an important idea here is that electrons that have the same N, L, and ML will be at the same distance from the nucleus of the atom, and they will have the same energy. Electrons with the same energy are said to be what we call degenerate, and your textbook will talk quite a bit about degenerate energy levels. So here are some radial probability distributions for the first 3 S subshells. So these are subshells that have L equals 0. So here we have N equals 1, that's the principal quantum number, L equals 0, or we'll write this in subshell notation as the 1s. And there we go, we have the position where it's most likely that the electron will be found, and that's going to be at the same radius as Bohr predicted in his model. Now we move out to the second shell, N equals 2, still an S subshell, so in subshell notation this is written as 2s. And what we see here is we have 2 peaks, and then we have a node. So the peaks correspond to distances where it's likely that we're going to find an electron. This is the most this is the most probable distance, and the node refers to a distance where we never find the electron. So no nodes for 1s, 1 node for 2s. Now we're going to go out to the third shell. We've still got an S subshell, so in subshell notation this would be written as 3s. Here is the most probable distance, and this time we've got 2 nodes. Notice that there's a reasonable probability that the electron will also be found at these distances, so occasionally the electron gets in real close. Okay, we start seeing a pattern with the number of nodes, and the number of nodes is given as follows. It is the principal quantum number minus the angular momentum quantum number minus 1. So you can see here we've got 1 minus 0 minus 1 0 nodes. 2 minus 0 minus 1 gives me 1 node, and then 3 minus 0 minus 1 gives me 2 nodes. So that's kind of, you can look at these curves and they often have questions like this, and you can decide what particular shell that it corresponds to. Okay, another way that these orbitals are often represented is in a three-dimensional diagram, which is referred to as a sort of like a probability surface. So what they draw is a three-dimensional representation of the subshell, which tells you where the electron is going to be a certain percentage of the time, and normally it's written as a 90% probability surface. So here's the 1s, and it's just a sphere, and that sphere has a radius the same as the Bohr radius. When we go to the 2s, what they're doing here is every time it changes color, that indicates that there's a node. So we see we get 1 node for the 2s. Most of the time the electron is out here. It's never at the distance represented by the change in color. So that's trying to show that we have 1 node there. When we go out to the 3s, we see the same thing. Most of the time it's on the surface of this sphere. It's a bigger sphere again, but this time we've got 2 nodes there where we have 0 probability of finding the electron. So we can look at these radial probability distributions for other subshell types. Here they are for some p subshells. So this is we don't see the p subshell until we get to n equals 2. So this is n equals 2, and now because it's a p, l equals 1, or alternatively in subshell notation that's called a 2p. We get no nodes there, so 2 minus 1 minus 1 gives me 0 nodes. Here we go out to the 3p. The most probable place chance of finding the electron is moved out. There's 1 node in here, but there's also some probability of finding it sort of quite a bit closer to the nucleus. So again, 3 minus 1 minus 1 gives me 1 node. And then we go out to the n equals 4. The electron's way out here most of the time. That's the most probable position. We've got 2 nodes, and then we have these couple of peaks in here where we also kind of have considerable probability of finding the electron. And again, you can see that 4 minus 1 minus 1 gives me 2 for the number of nodes. 4 minus 2, get it right, minus 1 minus 1, 2 nodes. Okay. So looking at the probability surface for a p subshell, they tend to look like this, where we have 2 what we call lobes. They're kind of like bun shaped, like that. And yeah, that's what they kind of, and then the nucleus is sort of in the middle here. So that's an accurate sort of probability surface for the p subshell. Typically though, we kind of will draw them as 2 teardrop-shaped lobes like that, because it's just kind of easier for us to draw them that way. Now, when L equals 1, that's the p subshell, ML equals minus 1, 0, and plus 1, and these ML values correspond to different orientations, and they correspond to orbitals that are directed along the x, y, and z axis. So an S subshell has L equals 0 and ML equals 0. There's only 1 orbital in an S subshell, and it's spherical in shape. A P subshell has L equals 1, and there are 3 values for ML, the orientation, and these correspond to orbitals that are directed along the x, y, and z axes, so at 90 degrees to each other. They have the same shape because the shape is determined by the L value, but they have different orientations. Now, when you get to a d subshell, which is L equals 2, you have 5 possible values for ml. And so a typical d subshell, there's only one that doesn't have this kind of shape, has this sort of like clover-like, 4-leaf clover kind of shape. It has 4 lobes to it, 4 teardrop-shaped lobes. There is the fifth one here has a slightly different shape, but you can see that these are clearly distinguishable from the p-type orbitals or s-type orbitals. So these ml values correspond to the different orientations of the d orbital. Now, when we go to F, it's going to get real weird because we have 7, right? So there are 7 different F orbitals. So an F orbital is what we get when L equals 3, and then ML runs all the way from -3 up to +3. And again, you can see the shape becomes more complicated. These have the same L value, they have different ML values, and that corresponds to different orientations, but it also seems to affect the shape. Most of them have these 8 lobes that is characteristic of an F orbital. But again, you can easily tell the difference from a diagram between an S, a P, a D, or an F. Now, you don't need to be able to draw these, but you do need to be able to distinguish whether an orbital is an S, P, D, or F. Okay, so the region of space where it is likely an electron will be found is described by 3 quantum numbers, m, l, and ml. And these are quantized values. They can only have certain specific values, and there are rules for deciding whether you have a valid set of m, l, and ml. What these numbers describe are, oh, that should be n, not m. What they describe are the general size, shape, and orientation of an orbital. How the electron is spinning within an orbital is described by ms, and ms can have values of +0.5 or -0.5. ms does not describe where the electron is, ms describes how the electron is spinning.